Well, we're going to let S be the objective function. And g of x the constraint. And g of x, we'll just call it g, because we're not going to name the variables. And g equals some constant is the constraint. So our goal then is to find a solution, so an ordered pair, ordered triple, ordered quadruple, whatever, that satisfies both the objective function and the constraint function. So we're going to talk about a couple of different methods in order to do this. So the first method is something we're familiar with from algebra. So method one is the substitution method. And the idea is we solve the constraint equation for a variable and substitute it into the objective function. So that's really the idea of the first method, is we'll have our constraint, and it is some function equals a constant. We solve that function for any of the variables, and we substitute that into the objective function, thus eliminating one of the variables and allowing us to find the maxima and minima. So let's go ahead and use this method on example number 1. So we want to minimize S equals xy times 2xz times 2yz, subject to the constraint x times y times z is equal to 4, and x, y, and z all have to be positive numbers. So this is going to be our constraint function right here. So if we take x, y, z, and we set it equal to 4, we're going to solve for a variable and substitute it into the other equation. Well, it doesn't matter which variable we solve for. It's entirely up to us. You're going to get the same answer whether you solve for x, whether you solve for y, or whether you solve for z, because in the end we're going to solve for all of them. So for no reason whatsoever, I'm going to solve for z because I feel like it. So if you did this method and you solved for x, you're going to get the same answer in the end. So I divide both sides by xy, and that gives me that z is the same as 4 divided by xy. We're then going to replace all of our z variables in our objective function with what they are equal to. So this gives me s is equal to x times y plus 2x times our z is 4 over xy plus 2 times y times our z once again, which is 4 over x times y. So then we can reduce a little bit. So in our second term, I have a 2x, and I have an x in the numerator and an x in the denominator that reduce out. And in our second term, I have a y in the numerator and a y in the denominator, and they reduce out. So multiplying our coefficients together gives x times y. 2 times 4 is 8 over y plus 8 over x. So after doing the substitution, we now have a function of two variables like what we were working with in the previous section, 15.3. So to find our maximums and minimums, what do we need to find first? Critical numbers. So the next thing we need to do is find the critical numbers. And remember, the critical numbers are the zeros of the derivative. So if I find s sub x, so my partial derivative of this with respect to x is going to be the derivative of xy is going to be y. The derivative of anything with an x is going to be 0. And we may not remember, but how do we find the derivative of 8 over x? So remember, the technique that we use is we move our x variable from the denominator into the numerator by making the exponent negative, and then we can use our power rule that we've been using for polynomials. And the power rule says we do what? We bring the number out in front and we subtract 1. So our derivative d dx of 8x to the negative 1 is going to be 8 times negative 1 x to the negative 1 minus 1. So that's negative 8x to the negative 2, or negative 8 over x squared, moving it back into the denominator. So that is our derivative, don't forget the square, of 8 over x. The other option that we could have used to do that, and it's really long, if we have two things that are divided, what rule can we use from calculus to find the derivative? The quotient rule, right? So remember, g f prime minus f g prime all over g squared. If you did that, you would also get the same thing. So it's worth noting we could have also used the quotient rule. So now we're going to do the same thing, but we need to find the partial derivative with respect to y. So s sub y is going to be, we have xy, so our derivative is going to be x. The derivative of 8y, we're going to do the same thing that we did here, so this time I will use the quotient rule. So my f would be 8, and my g would be y. And remember, the quotient rule is g f prime minus f g prime all over g squared. So I didn't leave myself enough room. We need to calculate f prime and g prime. Well, the derivative of a constant is always 0, and the derivative of y is going to be 1. So that would give us y times 0 minus 8 times 1 all over g squared, which is y squared. And we simplify, anything times 0 is 0, so we get negative 8 over y squared, which we'll note is the same thing we got for the other one for x, because 8 over y and 8 over x should have the same derivative, right? So whether we use the quotient rule or our exponent laws and the power rule, we get the same derivative either way. So we now have our two equations, so we need to solve the system of equations. We have x minus 8 over y squared is equal to 0, or y minus 8 over x squared is equal to 0. So once again, there are many methods that we could use to to resolve this. So substitution, I'm going to solve the second equation for y, giving me y equals 8 over x squared. And then I'm going to substitute that into the first equation. And that gives me x minus 8 over, well, my y value is 8 over x squared is equal to 0. So we can make negative 8 into a fraction by putting it over 1. And if we have a fraction divided by a fraction, we multiply by the reciprocal. So we get negative 8 over 1 times x squared over 8 is equal to 0. Our 8's reduce out, and we get x minus x squared is equal to 0.
Professor Peterson, what happened to the squaring on the y?
So now we factor, and we have x times 1 minus x is equal to 0. And our two solutions are x equals to 0, or 1 minus x equals 0 gives us x is equal to 1. So then we could find our corresponding y values by putting them back in. We'll notice if we try to put 0 in up here, 8 divided by 0 squared is undefined. So we're only going to get one critical number, which is 8 over 1 squared is going to give us 8. So then we get our critical numbers are 1 and 8.
Is my audio on?
Okay. So now we've done all of this stuff to help us find our critical numbers. We'll also notice there was something else that happened with x equals 0. If we go back to the very beginning of the problem, what was our requirement for x, y, and z?
So.
What did x have to be?
Mr. Peterson.
Bigger than 0. So x could not be
Pearson.
0. All right, so now
I can hear you.
we found...
Someone's trying to ask a question.
You guys hear me?
Yeah, we
Peterson,
can't hear each
Yeah,
other.
I hear you.
I think he can hear us.
So he's
This was supposed to be squared.
he's talking, but he
Right.
can hear us.
Yes. All right, so we plug this in and we get 8 over x squared squared. So that's going to give us negative 8 over 1 times x to the 4th over 64 is equal to 0. So now we get to reduce. Our 8 and our 8 reduce out, and we get x minus x to the 4th over 8 is equal to 0. And we're still going to factor the same way we did before. We still get the x equals 0, but now we have 1 minus x cubed over 8 is equal to 0. So this gives us our two equations, x equals 0, or 1 minus x cubed over 8 is equal to 0. So we're not going to worry about the x equals 0 solution because x has to be bigger than 0. And we add x cubed over 8 to both sides. 1 equals x cubed over 8 times 8 times 8. So we get x cubed is equal to 8. And we take the cube root of both sides. And the cube root of 8 is going to be 2. So now finally, we take our 2 and we substitute it back into our equation for y to get y equals 8 over 2 squared. So y equals 8 over 4, which gives us 2. So our critical number then is 2, 2, but we actually still need to figure out our z a little bit later. But before we do that, we're going to use this as our critical number to help us determine if we have a maximum or a minimum. But let's go back to our constraint. If we have x times y times z equals 4, now 3, we're going to use the constraint to find z. So our constraint is x times y times z is equal to 4. And if we know x and y, so if we know x is 2 and we know y is 2, we're going to have 2 times 2 times z is equal to 4. Or in other words, 4z equals 4. Divide by 4, divide by 4, and we get z equals to 1. So then, finally, we're going to have our point is 2, 2, 1. If we wanted to verify that it was a minimum, we would need to calculate our matrix that we used last time to do so. And in order to do that, we needed to know more partial derivatives and evaluate them at certain points. So we have our s sub x is equal to y minus 8 over, or it's x minus 8 over x squared. And we had s sub y is equal to x minus 8 over y squared. So then s sub xx, and remember, if we want, we can rewrite this as negative 8x to the negative 2. The derivative of y is going to be 0. The derivative of negative 8x squared, we bring the 2 down in front, or negative 2. So negative 2 times negative 8 is positive 16 x to the negative 3, which would be 16 over x cubed. S sub yy, same thing with this. We're going to get 16 over y cubed. And then finally, we need our mixed partial. So x sub xy, we're going to get 1. And notice if we did it in the other order, our mixed partials are always equal. So the derivative of s sub x with respect, or s sub y with respect to x is also 1. So then we find our matrix is going to be s sub xx times s sub yy. So 16 over x cubed times 16 over y cubed minus 1 squared gives us, what is 16 squared? That is the question of the hour. And we get 256 over x cubed y cubed minus 1. And if we put in our points 2, 2, 1, or in our case 2, 2, because this only involves x's and y's, that's 256 divided by 2 cubed times 2 cubed. And that is going, oh, take away 1. So then we have 256 all over 2 to the third times 2 to the third, take away 1, and we get 256 over 63. No, that is not the right number because I have a typo. I'm like, that doesn't seem right. There we go, much better. We get 3. So now we need to remember what our rules were for finding our maximum and minimum. So we have here our h is positive, so we're in cases 1 and 2. So for it to be a minimum, we need f sub xx to be bigger than 1. So that's going to put us in exactly case number 1 here. Because we calculated f sub xx up here. F sub xx is 16 over x cubed. So s sub xx evaluated at x equals 1 is going to be 16 over 1 cubed, which gives us 16. So our h is positive, which we had here, and our f sub xx is also positive, which we found here. So indeed, that point is a local minimum, as we saw. So then that tells us that the local min is at 2, 2, and 1. So in our blank lecture notes, you may have found that there was an Excel spreadsheet that actually has a graph of this problem. We didn't need the negative x values, but they're there. For us to take a look at. And so we'll notice at our point, we get our charts that look like this. All right, so let's head back to our next example. That is not the right section. There we go. So the substitution method works, and we've done things like that before in algebra classes. It turns out that there is a much better way for us to maximize and minimize problems. And the way we are going to do that is called the Lagrange Multiplier method. So the Lagrange multiplier method says to find the extrema of a function f of xy subject to the constraint g of xy equals 0, we construct the Lagrangian function, which is a new function of 3 variables, which is f of xy minus lambda times g of xy, where lambda is a new unknown called the Lagrange multiplier. If you're curious, that symbol lambda is a Greek letter. And stands for Lagrange multiplier. The candidates for relative extrema occur at the critical points of the Lagrangian. That is, we take our partial derivatives and we solve the system of equations in x, y, and lambda. So it's worth noting that this can be generalized to more than 2 variables. So if we have 3 variables, for instance, then we would have our Lagrangian would be L of x, y, z lambda, and we would set the 3 partial derivatives equal to 0 and use g of x, y, z equals 0 as equation 4. So if we had 7 variables, we would have a system of 8 equations. But the idea is that this generalizes very well, whereas substitution does not generalize well. Because if you try to substitute 7 equations into one other equation, it starts getting really circular, and that is problematic. whereas this gives you a direct method that we could also find methods of numerically approximating, which sometimes is better than trying to actually solve the system. So we can do this for pretty much everything. We're going to do this same problem again, but this time we are going to use Lagrange multipliers. So the first step for using our Lagrange multipliers says that we are going to construct our Lagrangian. So we have 3 variables this time, so we're actually going to have our Lagrangian have 4 variables, x, y, z, and lambda. And our Lagrangian is f, which is our objective function, and g is our constraint function. So our Lagrangian is going to be xy plus 2xz plus 2yz minus, and then notice it tells us that this has to be equal to 0. This equation is not equal to 0. So xyz equals 4. So we would minus 4 minus 4. And that would give us that xyz minus 4 is equal to 0. So then this would be our g of xyz. So then we would have lambda times lambda times xyz minus 4. So we always have to have our g of xy has to be equal to 0. So we solved all of that. We set the constraint equation up and set it equal to 0. So now if we multiply this out a bit, we end up with, I'm just going to write L now, xy plus 2xz plus 2yz minus lambda xyz plus 4 lambda. So now we need to set up the system of equations. So that was our step 1. Step 2 is we set up the system of equations. And so remember, our equations are, we set all of the partial derivatives equal to 0, and then our constraint equation that we came up with. So let's find L sub x first. So we're going to get y plus 2z, third term is 0, minus lambda yz, and then the derivative of 4 lambda is going to be 0. So that gives us our L sub x, which we're going to have to make equal to 0. And we do L sub y, which is going to be x. The derivative of 2xz with respect to y is 0. The derivative of 2yz is going to be 2z. And then the derivative of lambda xyz is going to be negative lambda xz, and the derivative of 4 lambda with respect to y is 0. So that's going to be our second equation. We have our third equation is L sub z is equal to the derivative of xy with respect to z is 0. The derivative of 2xz is 2x. The derivative of 2yz is 2y. The derivative of negative lambda xyz is negative lambda xz. And the derivative of 4 lambda is 0. And then lastly, we have our last equation, which is x, y, z minus 4 is equal to 0. And we need to solve this system of equations. So now we need to solve this in any way that we can. So one thing that we may notice in this is this last equation is equivalent to x, y, z is equal to 4. And in this system of equations...
Mr. Peterson?
Yes, sir.
I have a question on the...
All right. So we notice that these terms right here almost look like this. We have a yz, we have an xz, and we have an xy. So what we're going to want to do is we're going to multiply this equation by x. We're going to multiply this equation by y, and this one by z. And if I do so, then these last terms will all be lambda x, y, z. So my new equation, if I multiply the first equation by x, my new equation 1 is going to be xy plus 2xz minus lambda x, y, z is equal to 0. My new equation 2 is going to be, when I multiply by y, xy plus 2yz minus lambda xyz is equal to 0. And my last equation, when I multiply it by z, is going to give me 2xz plus 2yz minus lambda xyz, and that's going to be equal to 0. And then I still have my equation 4, which is xyz is equal to 4. So I can now keep working with this, but I notice something that's kind of interesting. If I look at equations 1 and 2, if I multiply equation 2 by negative 1 and add it to equation 1, this will eliminate 2 of those terms. So I'm going to go negative equation 2 plus equation 1 to replace equation 1. So if I multiply all of this by a negative, it's going to be negative xy minus 2yz plus lambda xyz equals 0. And I'm going to add that to equation 1. Minus lambda xyz, and that is equal to 0. So when I do this, I have my terms here reduce out, and my two terms here reduce out, and that leaves 2xz minus 2yz is equal to 0. So now I can actually solve for some variables. So I have a common factor of 2z in both of them, so I factor out my GCF of 2z, and that gives me leaves x minus y is equal to 0. Well, if that's the case, my two equations are 2z equals 0 or x minus y equals 0. Well, we solve this one and get z equals 0, which we can't have because x, y, and z have to be positive. Or we add y, and we get y is equal to x. So this tells us then that in our solution, y and x have to be the same value. Okay, so now we can go back and use a different equation or something else to solve for another variable. So if y and x have to be the same thing, let's take a look at equations 2 and 3. So equation 2 with y equal to x gives me, so x times y would be x squared plus 2xz minus lambda x squared z equals 0. And equation 3 would be 2xz plus, if y is the same as x, 2xz minus lambda x squared z equals 0. So once again, we could, after substituting this in, subtract these two equations. So if we do so, subtracting each of these, we would notice these are equal and opposite, and these would be equal and opposite if we subtract. So that would leave us with x squared minus 2xz is equal to 0. We factor out our common factor of x, leaving behind x minus 2z is equal to 0. So then we would have x is 0 or x minus 2z is equal to 0. So in that case, we would have x equals 2z, or solving for z, z is equal to x divided by 2. So if y is equal to x and z is equal to x over 2, we can finally use equation 4. So equation 4 tells us that x times y times z was equal to 4. So we substitute those values in. So y is the same as x and z is x over 2, so that's x times x over 2 is equal to 4. So we get x cubed over 2 equals 4. Multiply both sides of our equation by 2, and we're back to x cubed equals 8. Take the cube root, take the cube root, and we have x is equal to 2. So now if x is equal to 2, y equals x, so y equals x gives us that y equals 2, and z equals x divided by 2. So that's 2 over 2, which gives us 1. So our x, y, and z are 2, 2, and 1. The same values we got doing the other method. So find this dimension. So let's draw our box. And bear with me because I am not the best artist on the planet. So we have a box that looks something like this. And we have our length, we have our width, and we have our height. So let's label some dimensions. So let's call this x, let's call this y, and let's call the height of our box z. So then our goal is we want to find the dimensions of an open-topped rectangular box so that the volume is 4 cubic feet and it has the smallest possible surface area. So the surface area of a box is the material that it would take to make it. So imagine if we were to cut this and lay it out flat like an unmade cardboard box, right? So based on my picture, if I were to do this, so my base down here in the bottom would have dimensions. This would be x, and this would be y, right? And then now imagine if I fold down the 4 sides that are there, it's going to look something like this. So then I know that this is going to be x, and I know that the top is also going to be x, and I know that these distances are going to be y and y. So the only place left is where we folded down the box, and that's going to correspond to these, right? So this distance is z, and then this distance would also have to be z. Well, if that's the case, now that I have all these things labeled, what is the area of each of these pieces of cardboard? Well, the one in the middle is going to be x times y, so this has area xy. The one above it is going to be x. Oh, I didn't label them. These are also z's. So that's going to have area x times z, and by symmetry, this one will as well. And then we have the two other sides of the box, right? And what would their areas be? Y times z. So that's going to be the surface area of all of these. So the surface area of the box is going to be the sum of all of those areas. So then S is equal to xy plus 2xz plus 2yz. And then our constraint is, well, what's the volume of a rectangular solid with side lengths x, y, and z? So our volume is our length times our width times our height. So in other words, it's x, y, z, right? So then what are we told the volume of the box needs to be? 4 cubic feet. So subject to, we need the volume x, y, z to be equal to 4. So our goal then is to find x, y, and z to make a box that has a minimum surface area and contains the volume that we were requested. Okay, well, it turns out we actually did this problem. This was exactly example number 1. Because if you go back and look at example number 1, what did it ask us to do? Or example number 2, or 1, they're both the same. Minimize S equals xy plus 2xz plus 2yz subject to the constraint x times y times z equals 4. So the problem that we actually did in examples 1 and examples 2 was to solve this problem. And we solved that x and y be both equal 2 and z equals 1. So from examples 1 and 2, we have x equals 2, y equals 2, and z equals 1. So the dimensions of the box would be 2 by 2 by 1, and that would make the box with the smallest surface area that has exactly a volume of 4 feet. So if you were trying to manufacture this box and the cost of material was uniform, then that would be the dimensions of the box that would hold 4 cubic feet of stuff that would have the minimum surface area, which would mean it would use the least amount of material. So that's one way that we can use Lagrange multipliers or maxes and mins to manufacture something in such a way that it will minimize the cost of the object. All right, let's take a look at example number 4, and we haven't done this one yet. So we're going to do the same thing, but this time we're just going to focus on the setup. So this one says a cylindrical can is going to be made to hold 1,000 cubic centimeters. The materials for the top and the bottom cost 15 cents per square centimeter, and the cost for the sides is 5 cents per square centimeter. Find the dimensions that will minimize the cost of the metal to manufacture this can. All right, so let's start with our cylindrical can. So if it's a cylinder, it's going to look something like this. And we want to use a technique similar to what we did in the previous problem. So the hint in this is that the top and the bottom cost 15 cents per square centimeter, and the sides cost 5 cents per square centimeter. So similar to what we did in the previous problem, we want to deconstruct this can. So in this problem, we laid it out flat because we wanted to find its surface area. So imagine if we have this can, what is it made out of? It has a top, a bottom, and the sides. So let's label some variables. So if we were to call the radius of the circle x and the height of the can y, if we were to look at the top and the bottom, we would have two circles. So there's my top, there's my bottom, and each of them have a radius of x. And what is the area formula for a circle? So that is pi r squared, but our radius is x. So for this, we're going to have that the area is, well, how many circles do we have? 2. So it's 2 times pi times our radius, which is x, squared. So our area is 2 pi x squared. So that's for our top and our bottom. So now we need to look at the side. So the side, imagine that we've taken the top and the bottom off the can. If I make a lateral cut up the side and lay it out flat, what geometric figure is it going to look like? It's going to be a rectangle. So from our figure, we know the height is going to be y. The question then is, well, what is this distance going to be? Well, that is exactly the distance around the circle, because the can goes around the circle and connects, right? So this distance is going to be the same as the circumference. And what's our formula for the circumference of a circle? 2 pi r, but our radius in this case is x, and this is our circumference of the circle. So then the area of this part is going to be 2 pi x times y. So we have the area of the top and the bottom, and we have the area of the side. But now we know what the cost is for each of these. So cost, we have our cost per unit area, and then we have a formula for our area. So to find our cost, we're going to have C, which is our cost, is going to be our cost per unit area, so 0.015, or 0.15, I said that in the wrong order, times our area, which is 2 pi x squared. So this is the cost of the top and bottom. Plus, we now have our side, which we know costs 5 cents per square centimeter, and we're going to have its area. So we have 0.05 times its area, which is 2 pi x y. So that is going to be our cost function. And then what is our constraint going to be? So we have our cost. Now we need a constraint. Our constraint comes from this. A cylindrical can is to be made to hold 1,000 cubic, that's not right. Should be cubic, I wrote square. Cubic centimeters. Volume is cubic centimeters. So, by the way, a cubic centimeter is equal to 1 milliliter, so this is a 1 liter can, is what it's saying. So then, the question then becomes, well, that's a volume. What is the volume formula for a cylinder? So in general, it is the area of the base times the height. So that's true regardless of what the base is. So if the base was a square, it would be the area of the square times the height. If it was a rectangle, we would use that. If it's a pentagon, it doesn't matter. So what's our area formula for a circle? Well, it's pi r squared in this case, but our radius is x. So it's going to be pi times x squared times our height, which is h. So we have our area of our base, which is pi r squared, times our height, which is this. And we know that our volume V has to be 1,000. So we end up with our...
I think the height is supposed to be y, right?
Oh yeah, y. Thank you. Of course. We would have found out in 1 second. And our height is going to be, so we have 1,000, which is in blue, I believe. 1,000 is equal to our pi x squared y. And that's going to be our constraint. So then we could then use this to find the dimensions x and y, so the radius of the circle and the height of the can, that would give us the minimum volume, or not the minimum volume, the minimum cost for a can that contains exactly 1 liter, which would really be our goal for this.